Aloha, Richard Halverson here. This is ITS388AL, and today I'd like to go over the third assignment, the Fibonacci generator assignment in that you were assigned in Chapter 4. Okay, so let me share my screen. Okay, and let's see. Let me pull up La Lima. Here we are, and we are in 388AL, and so our lessons. Let's see, we're somewhere around week 5 or so. Let me see this. Okay, yes, this video is going to go here, and you've gone through Chapter 4 last week, presumably, and today we're going to work on assignment 3. So this is assignment 3, and it's to write a program that calculates the Fibonacci sequence up to a maximum value of a value that is defined here, 75,000, it looks like, and it asks you to store the sequence in an array, okay, a double array, a double word array, and you got to make sure you allocate enough space. Okay, so and this gives you some numbers here to check with. If this is the max value, you should get a number this high, which would be something like the 25th or the 24th or what, 25th Fibonacci number. All right, so so I'm going to get started here. First of all, I'm going to download. No, let me go back to here, and let me go back to week 4 because that's where. Okay, so so you should start by downloading this project here, and then make sure you download the Irvine libraries too. So I'm just going to do that from scratch, and I'm going to save as on the desktop, on my desktop here. And I'm also going to make sure I got these Irvine libraries. I'm going to save those also on the desktop. All right. So now I've got, I'm going to put this here. So now I've got this project that I'm starting with in these Irvine folders here. So I'm just going to start with this project and extract it and put it on the desktop here. And here it is. Let me open it up. And it seems to have opened up. I know I got 2 of them here. And so let's go in, and it's this add to project. Let's just start it up. Let's see. So it ended up opening up over here. Let me move it as soon as it's done loading. Here we go. All right. So let's just let's take a look at this add to some program. Let me just, I think I can double click on it, and it opens up here. Okay, so this is a simple program that adds 5 and 6 and quits. So if we build this, and I know this isn't going to work because we don't have the Irvine.lib files, which are this file, and so that's because we didn't do anything with this other thing. Let me open this up, unzip this, extract all. And I'm just going to extract it on the desktop here. I'm sorry that took so long, but here we are. And so we're inside this folder here, and these are the files that the assembler wants to have access to. So let's figure out what the address of those files are, and here it is. It's in my desktop. So I'm just going to copy this, and then I'm going to go back to the project here, and I'm going to go to project properties, and over here I'm going to go to the linker. There's a couple places I can do this, but I'm just going to go to the linker here, general, and right here, normally you would install these right at the root of your C drive, but let's not do that. I have mine on the desktop, so I put that path to that directory right here. Click OK. And now when we build this, it should work. Build. Okay, now to run this, I'm gonna. This is a breakpoint. I'm gonna put a breakpoint there, and I'm gonna put a breakpoint there. All right. So let's see. What are the different ways I can run this? I can first start debugging. Okay, I'm just gonna run this, and what pops up? This pops up. And let's see, I've got a memory map that pops up. I can show you this. I can show you this in a moment. So I've gotten rid of that. Okay, so we're at this point right now, and we're about to move 5 into the EAX register. Right now, the EAX register is right here, and I have this register as window. If you don't have the register as window down here, you can go to View. Is this where you know? You go to Debug, Windows, and you go down here to Registers. This is where this will open up the registers window if it's not open already, and this here opens up the memory window if that's not open already. Okay, and we're going to do that in a moment. But anyway, all right. The other thing I want to see here is if we're able to step into step into. So let's do F11, and now the 5 into EAX has executed, and that's why we see 5 down here. And then let's do step into again. And now we've executed this add EAX6, and so that's why EAX now has B in it, which is 11. And then we're ready to quit, and we can just quit if we want to. All right, so this is the how we can start, and I just and it compiles it or assembles and everything. And so the first thing I'm going to do is I think I'm going to change the name of this to change it to Fibonacci, Fibonacci. Okay, Fibonacci. I'm going to close this, and let me okay. And let me change this to Fibonacci. All right, and I'm just going to run this again just to make sure that that worked right. Okay, built fine. And the other thing I'd like to go over today is I'd like to introduce us to the listing file. Here's the listing file, Fibonacci, there it is. Here's the listing file. I'm going to open that up. And so when the assembler assembles your program, this is the machine code. This is the machine. These are the actual bytes that get uploaded into the program memory in the code section. And this is the first instruction, which is move the value 5 into the EAX register. And this instruction here is add the value 6 to the EAX register. And then this does some stuff where it returns control to the operating system. So anyway, we're going to be looking at that. So let's start doing Fibonacci here. So I'm going to let me bring this back up, and let's go to the programming assignment again. Oh, I had it up already. Does it describe here what it does? It doesn't really describe here what it is, so I will just describe it myself here. Let me bring up a pen. Okay, so the way the Fibonacci sequence works is you start out we can start out with 0, and then we go, and then it's 1. Okay, so those are the first two numbers, and then what we do is for the next number we add the previous two numbers. So 1 plus 0 equals 1, and then 1 plus 1 equals 2, and then 2 plus 1 equals 3, and then 3 plus 2 equals 5, and then 5 plus 3 equals 8, and then 8 plus 5 equals 13, and then 8 plus 13 equals 21, and so on. So you see this number, this next number, is going to be the one just before it plus the one just before that, and that's what's going to go in here. Okay, so let's write a program to do that. So let's start out with, well, I'll tell you what, I like to start out with something. So I happen to go back here to the slides for chapter 4, and it's like the 71st slide here, summing an integer array. Okay, so I'm gonna, this is actually not correct. We need to have, we need to have this main proc in here, and we have this exit process proto, and then the data section goes right here, and then the code section is after that. Okay, so so I'm going to just copy this part, because what this is summing an integer array. So this takes this, adds it to this, and then adds it to this, and adds it to this. So that's, you know, we're getting close. Anyway, so first I'm going to copy this data part. Copy. And let's see if what happens if I just paste it right in here. Let's see what happens. Paste. Ooh, that looks fine. Okay, and then this code part, we have to have this main proc here. So we're going to replace these two statements, basically, with these all the way down to loop. So I'm going to copy this. And what happens if I paste it right here? Paste. All right. We've got a move EDI. We've got a move ECX. We've got a move AX. We've got an L1 label here. We've got an add. We've got an add EDI. We've got a loop instruction. Okay, so what this does is this loads the EDI register, which is it's an index register. It's used to address the memory. It's used as an address for the memory. And we load into EDI, we load in the offset or the starting point of array, of this int array. So now EDI is pointing to the first word in the int array. And then what we're going to do is this is the counter, because we're going to do 4 of them, okay? What is the length? The length of int array? Well, it's 4. It's 1, 2, 3, 4. That's not the size of int array. The size of int array is the length of times the size of the type, or the number of bytes in the word, which is 2. Anyway, so we want the number of elements, which is the length of, and so that goes into ECX, and that's going to be our counter. And then we're going to start out by zeroing out the accumulator, or this AX register. And then what we're going to do is we're going to grab the contents pointed to by EDI. So we're going to be grabbing this value, and we're going to be adding that to the AX register. And then we're going to, okay, so that's adding, because we're going to start with 0 and add this, and then add this, and then add this, and add this, and we're going to end up with a final value in this AX register. And then we're going to increment the EDI register so it points to the next one. First it points to this one, then it points to this one, then it points to this one, then it points to this one. So each time we're done adding, we have to add, and what we have to add is the number of bytes in each one of these words. So that's what this type keyword is here. With this translates this to what this would be as 2. This a word is 2 bytes, and that adds 2 to EDI, and then we go here, and what this instruction does is it decrements ECX by 1. That's what it does. It decrements ECX by 1, and if the value after it's decremented is 0, then it drops down through. If it's not 0 yet, it goes back up to L1, and it does it again. So this is going to do it each time it decrements ECX by 1, and ECX starts out with 4, so it's going to end up doing it 4 times. And so it's going to add this one. It's going to do this add 4 times. So it's going to start with 0, add this, add this, add this, add this. Okay, so let's see this thing run, just to see it run. I'm going to build the solution. And it looks like it's okay. So now I'm just going to hit, let me put a breakpoint. We might as well put it right after we add and right before we increment EDI. Okay, then I'm going to put it down here so we can see how it ends. Okay, so let me hit F5. I hit F5, and it starts up. And I guess, okay, so here's what it starts out. So we're down. EDI has got the offset address of the int array, and so EDI is going to be 0. This is the this is the where the int array starts, and so this number was filled in at link time, and I'll talk more about that later. ECX should have the length of the array, which is 4, and then we moved 0 into AX, and then we added what is that EDI, and what EDI as okay. Now it's time to look at the memory. So I'm going to do debug Windows memory 1 is fine, and it usually initializes right at where the data memory is, and so here's the 1. Oh, 100, yes. 0100, and then it's 0200, because it's Indian, little Indian, remember, and then it's 0300, 0400, and that's what 0, 0, 1, 0, 0, 0, 2, 0, 0, 0, 3, 0, 0, 0, 4, 0, 0. So that looks right. And then so this adds 100 hex 100 to AX, and so AX should have hex 100, and it does. But the problem is there's this garbage up here in the upper E part of AX. So so I'm going to do this right now. I'm going to turn this off, and I'm going to make this EAX. I think that'll work. It might not work because no, I better not take a chance. Okay, let's build it, and F5. All right, 0, 1 there. That's loaded up. Oh, see, now it looks nice. Okay, so see, this looks nice. Okay, so do F1. Now ECX is down to 3, and you see EDI is pointing to the next one. It's pointing to this, and so now it's and then that's before it's incremented, and then it's incremented F5, and now it's 6, and then one more, and now it's A. So yes, that's 10. That's the last value. And ECX is 1, and we're right before the loop instruction. So this loop instruction is going to decrement ECX. It's going to go down to 0, and it should stop right here. So let's F1 one more time, F1, and there it is. ECX is 0, you see. EAX has the last value. Is that the last? Yes, that is the last value. And all right, so that's how this works, and this is how we can verify the memory. All right, so let's change this to what we're going to do for Fibonacci. Okay, first of all, in the data here, let's make this a Fibonacci array, fib array, and let's do double words because we're gonna get some pretty big numbers, and we're gonna have some large number of them. It's a pretty big array. Let's just make it I don't know, 50, and we're gonna dupe, and we'll make it's all zeros. We're gonna initialize it as all zeros. Okay, so this is our Fibonacci sequence array. And then we got the code section here, main proc, and let's see. So first of all, okay, I'm gonna initialize the array. Where did I write that someplace? Yes. So I'm gonna call okay, so let's have this be the first one. So I'm gonna initialize the 0th element and the first element. Okay, I'm just gonna write those manually, and then I'm gonna position the thing right here, and then my code is gonna start by adding the last 2 and putting that number there. Okay, so I'm gonna say EDI is going to be the offset of fib array, and right now I'm just going to do a counter. Okay, so you're going to actually do something different. You're going to make it be a max value thing there, and I'll get to that. But let's just try the counter idea first. And so I'm going to initialize everything. Okay, so this is pointing to the first one, And it's pointing to the beginning of fib array, and I just want to write, I'm going to write 0 in there, okay? So I'm just going to move, and I got to do this, okay, so I'm going to try to do this, ESI, and I'm just going to put a 1 in there, okay? 0, to initialize it as 0. And so this is initialize 0th fib number. Okay, and then I got to increment. I got to add, and I got to add the whatever the size of this is to point to the next one. So it's going to be add to ESI type of fib array. So so that's going to add 4 to it because D word is 4 bytes. Increment ESI to next element. Okay, then I'm going to move, just going to manually move into ESI a 1. Okay, by the way, this is not going to work, and I'll fix it later, but you'll see it first. Okay, this is initialize the first fib number. Okay, and then we want to initialize the loop counter, and let's just do it. Let's do it 20 times. Let's do it 25 times. And all right. So now, now that that's all set up, let's. I guess we don't need this. Let's. Okay, so this is the core of our loop right here. So we're gonna go. First of all, let's grab the second. First of all, let's grab. Okay, so we're doing right here, right? So let's grab the 0. So that's 1, 2. That's 2 back. Okay, so I'm gonna do move into EAX, move into the accumulator. I want to move in ESI, but I want to subtract 2 times the size of each word. So that's 2 times the size of each word, and I want to subtract that value from ESI because I don't want to be pointing to right now. ESI is pointing to this number. I want to go back 2 and grab 1, 2. I want to grab the 0. So that's going to grab the 0 and put it in EAX. Okay, and so I'm going to say grab 2 fibs back. And then I want to add to EAX ESI minus just 1 times type fib array. So that's just 1 back. So add 1 fib back. And of course, I don't really need the 1. And then, and that's the number. So I want to just store that number. So I move into ESI, EAX, EAX. Store sum into this fib. Okay, and then I'm going to increment EDI, ESI by the size of fib array. Okay, so this is gonna increment point to next fib slot. How's that? And then this is gonna loop. And so each time it loops, it will calculate a new EAX and store it where this is going to be no, never mind. Never mind. This is not. We're incrementing the pointer. We're not incrementing we're not adding to a value out there in memory. We're actually just adding to this register. And we're adding 4 to the register. All right, so that loops that, and so let's build this and see what happens. Okay, we did get an error, failed. So let's look at the error list, and we see that we've got a couple of invalid instructions here. We've got line 14 has got an invalid instruction, and line 16 has got an invalid instruction. So that would be this instruction and this instruction. The problem is when we're loading 0 into whatever it is that's pointed to by ESI, we don't know if what's pointed to by ESI is a byte or a word or a double word or a quad word or whatever, or just a double word. So we have to tell it. And so the way we tell it is we say it's a D word pointed to by that. So this prefixes this, saying this is the address, but it's actually a D word that this address is pointing to. So put a D word 0, in other words, put 32 bits worth of 0 into the address pointed to by ESI. And then we have to do the same thing for the next one too. All right, and that's because it doesn't know what size operand it is. And the reason is because these Intel processors have stayed compatible, backward compatible, all the way starting with the 8080 or the 4004 series in 1971. They invented the microprocessor, and it was the 4004, and it was just a 4-bit microprocessor. Okay, and then as they added bits, as they expanded the bus size, pathway to memory, they wanted to keep it backward compatible. So every now and then it's ambiguous, and you gotta actually specify. All right, let me build this. And now it works. And so let's execute this. I can just do F5. This is going to go 25 times, I guess. Okay, so what happened? Exception thrown. Access violation. Okay, let's figure this out. Let me close this. And turn this on. Oh, there's some errors, something. Didn't initialize anything in memory. All right, let me just shut this off and see if I can eyeball this. EDI. Oh, wait a second. Oh, we're doing ESI, not EDI. ESI is the operator of the fib. Is this okay? EDI. I think that is it. Let me just build it. And let me F5. Okay, much better. Okay, we're down here. ESI is the offset of fib array. We loaded 1 in there. Oh, we've loaded 0 in there. We've loaded 1 in there. And now, we need to increment ESI one more time. we need to increment this one more time, because this is always pointing to the next one. This is always pointing to the open one. So we need to, so this is pointing to the open one. And then this goes back 2, this goes back 1. Okay, this should work. Let's try this one. Let's build it. And all right, F5. Okay, so we're down here, and we see that the first one is initialized, and then we see the next one is initialized. And remember, it's little endian, so the lowest order byte is a 1 and should be in the next 3 orders of bytes are zeros. And this is the third one. So we have seen this execute, and we've seen this execute, and we've seen this execute. Okay, so that's why, so the third one's got a 1 there. And then we're going to add, we haven't done this yet, but we're going to add the size of fib array to ESI. So right now, this ESI is pointing to the one it just wrote to, and that would be that one. I guess that's this byte right here it's pointing to. Anyway, so let's continue this. And now we've written the 2, and EAX is, that's what it just wrote. And we're down to 1.8 because we started out with 25, which is 1.9, and now we're down to 1.8. And let's just hit F5 a few more times. 17, 16, we can see them being added in over here. Okay, and now we're at, and so here we see this is the lowest order byte, the second lowest, third, fourth, and here we see it, you know, a regular way. We're at 0B, and we're going up to 25. Okay, let's press F5 again. And so we're at 7, 6, 5, 4, 3, 2. I believe this is how far we go. And this is a 12511. If we actually do a search, let's search for hex calculator, no, hex converter. Let's see what this does. This is one. Okay, insert hex value. What is the hex value? It is 12511. 12511. Ah, it's 75025, and that's how far we wanted to go, according to the assignment right here. And we see that if max val is 7500, we go about 25 when we get to 75025. All right, so now, so let's just F5, 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 and we're done. So, but the thing is you don't want to end, okay? You don't want to end by a count. You want to end by a value. So I'm gonna adjust this program a little bit to show you how we might get closer to a program where we are going to terminate the loop based on a comparison of 2 values rather than just a count. So, but I'm still going to do count. So I'm going to create a variable here called max count, and I'm going to EQU. I think I got to do a colon. Max count EQU, and I'm going to have it be 25 because I'm going to have it loop 25 times. And then instead of having this fancy loop instruction here, what I'm going to do is I'm going to start up by loading this no, I'm going to load it with 0. I'm going to start counting with 0. And then each time I go through a pass, I'm going to increment. I'm going to increment ECX. Okay, and that adds 1 to the count. 1 to the count. And then I'm going to compare. I bet I should probably, you need to get used to looking up, let's see, vital source. Do I have, does it know my, does it remember who I am? Is this right? It seems to be right. Yes, okay. So let me continue reading this, our textbook. And if I go all the way down to the appendix, see, we are in chapter 4 right now, and we're learning about data-related operators and directives. But I want to go back to the the instruction set. And let's look at the instructions. Okay, here's the instruction set. This is in the back of your book. And I'm going to look at the compare operation. CMP, compare. Okay, and all of the compares the destination to the source by performing an implied subtraction of the source from the destination. So of the source from the destination. Okay, so anyway, I'm going to do compare CMP. Compare ECX is going up, ECX, and I want to compare that with max count. And then see if ECX has reached max count. And if it has, the result of that comparison is going to be, it's going to be a positive number. Until ECX reaches max count, this comparison is going to yield a negative number because we're going to have the first time it's going to be 0. No, it's going to be like 1 minus 25. Well, that's a negative number. 2 minus 25, 3 minus 25, 4 minus 25, all the way up to 24 minus 25, still a negative number. 25 minus 25, that's a 0 is considered a positive number. So what we want to do is jump if it's positive, or jump if ECX is above. Actually, I guess it must be above. Must be. I bet you it does it at 26. Anyway, what I'm looking at here is the JA instructions. J condition. So I want a J condition label. So I want to do JA. Jump if above. Jump if above. That sounds kind of silly, doesn't it? But I want to jump if ECX is above max count. Jump up above. And I want to jump to L1. Okay. And I don't want to do this anymore. So I'm just going to comment that out. I don't even want it anymore, so I'm just going to get rid of it. And then right here, I want to have an L2. How is this? Oh, no, wait a second. No, if ECX, oh, if ECX is bigger than max count, I don't want to jump back. I don't want to jump back here. I want to jump out. So I want to jump out of the loop. If ECX is not above max count, then I want to do this. And what this is adding it's this. This has got to go down here. And L2 is, we're done. Okay, so here's how this works. This thing, it starts with ECX equals 0, and then it does the adding. It grabs this one, adds it to that, saves it here. And then it increments the counter, and then it compares to see if the counter is above max count yet. If this counter has reached max count, if this ECX is above max count, then it jumps JA, jump above, to L2. So it jumps out over here. Otherwise, it does this. It adds, it increments ESI, so it points to the next Fibonacci slot, and then it has to jump back to. This is an absolute jump, L1. So no matter what, it jumps. So here, if the comparison is ECX is greater than or equal to max count, it's going to jump out to here. In other words, it's going to jump over these two instructions. Otherwise, it's going to go ahead and increment ESI and jump back. Okay, so this should operate exactly the same. And let's just make it go up to 15, smaller number. I guess I was running the whole time. Let me turn that off. And let's stop here. And that's fine. Okay, let's build it. Oh, it failed. What failed? 10, line 10. What's the matter with line 10? Oh, max count equals, there's no colon. Let's build it. Okay, it succeeded. So let's do some F5s here. F5. Here we are. Okay, so we've loaded up 1 and 2. Oh, 0, 1, and 2. And so, yeah, EAX is 1. ECX is 1 because we've only done one of them. And ESI is pointing to whatever 4048, which is up the next one. Oh, it's not pointing to the next one yet. It'll be pointing to the next one after this is executed. So let's do another F5, and it comes back to here. And now 2 just got stored out. You see right here, 2 got stored out. And that's what the 2 is here. And we've done 2 of them. F5, 3 of them, 4 of them, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, ECX is going to go all the way up to whatever max count is. I'm going to show you I'm going to take a break, and I'm going to show you the project listing. You should look and see the project listing. You can see how it is compiled, and this is how it is compiled, and this is what we're running. Okay, this is what compares ECX with max count. Max count is 15, which is 0F, and so we see that's what this is. It's 0F. This is comparing ECX with 0F, and this is what the jump to jump if above to L2 is, and this is relative, so it's just I don't know if it's relative or not, but it's oh, jump 2 is just 5 ahead, so yeah, 1 2 3, yeah, it jumps to, it actually sets it to here because that's the next instruction. That's what L2 is. Otherwise, it jumps back to L1, which is ED, which is back to here. So that's a negative number, obviously. All right, so let's go back to here and keep on running this thing. Continue. Oh, I guess we're at the end. Okay, so so we can run this again. Can I just do F5? Yes, so it's going to go 15 times until this gets up to F. F. Okay, now the comparison has just been made, and so if we look at these flags, I don't know which one's the carry flag, but one of these is the carry flag. No, yeah, the carry flag, the borrow flag, and it's going to be 0. Something's going to be set to 0. It's right here. It's already done the comparison. We're at F. So it did the comparison, and so we can see it's carry flag went to 0, and it's going to jump out to here, and we're done. And okay, so this is how we can stop it. We have a variable here that we're stopping it at, and what you're going to do is you're going to change the stopping. Instead of stopping when the counter reaches 15, this is the counter reaching 15, you're going to stop when the accumulator, the EAX register, when the EAX register, when that reaches when that reaches 750,000. So you keep this accumulator keeps getting bigger and bigger. This EAX. So write down. You can still have the counter if you want, but you don't. But this comparison is not going to be the counter with this. It's going to be the accumulator with whatever this here, 7,500. And if the accumulator ends up being bigger than that 7,500, then it jumps out. If it's not bigger than the 7,500 yet, it goes back up here and goes through another iteration. All right, so I think that's a pretty good start. Also, when you're done, I would like to see the listing file. I'd like you to hand in I'd like you to hand in this one, LST file. So open this up, copy this, and then paste this into here. Is that what I did? Oops, turn this on. Yeah, it looks like that's what I did. Okay, this is a different solution. In this solution, I actually use registers. I save, the problem, just so you realize, one problem with this solution is that every iteration, we are accessing the memory 3 times. We're accessing the memory 3 times. Instead, we could have the solution where we save the second to the last and the last, we save them in registers, like we use the EBX register and the EDX register. And then when we do the calculation, we do the calculation on registers, and then we only have one access to the main memory. And that would be faster. It might not be a more compact program, but it would certainly be faster. So anyway, I hope that helps, and so good luck with this Fibonacci program, and thanks for watching.